pops up the old one. There it goes. Okay, we'll get that out of there. Okay, so as you saw on the syllabus, the list of topics for this course, we start out with some fairly basic concepts, but we do that for a couple of reasons. One is it's nice to have the review, and two is I found that many of the mistakes that people make in the more advanced topics and the algebra side of it is because they don't really understand what they're doing with the simplest numbers. You know how to do it, but you don't really know why. And so that's what I want to do is I want to go back as we go through those and talk about why we do things the way we do. To give you an idea of what I mean by that, let's take a look at one of our most basic, or probably the most basic topic in math, but also one of the most misunderstood, and that is, what is a number? Show of hands, if I put a 4 up here, how many of you would tell me would say that that's a number? Most of you would, right? Some of you are a little shy, you know there's probably a trick to it, right? But really, that is what we call a numeral. It is just an amount. To truly be a number, it has to have two parts. It has to tell us how much, but it must also tell us of what. So instead of just 4, maybe we have 4 cows. Now it's truly a number. We have the amount, the 4, which I'm going to call the count, tells us how many. And then we have, what is it that we have 4 of? I'm going to call that the name. So in this case, it's cows. Now, I'm not doing this because I'm one of those teachers that requires you to label everything or I'm going to mark it wrong. That's not my purpose here. But the two parts of a number, that label or that name, is very, very important in how it interacts with our math operations. So let's take a look at our two most basic math operations, which are addition and multiplication. You might be thinking, where did subtraction go? I thought addition and subtraction were our most basic. Well, if you get really deep into number theory and math theory, subtraction isn't an operation. It's part of addition. We're not going to get quite that deep, but when we talk about integers, we might a little bit touch on that topic. But addition and subtraction are really the same process, just one's going forward and one's going in reverse. So any rules or items that we mentioned for addition also apply to subtraction. And the same with multiplication and division. They're really the same operation, just one's going forward and one's going in reverse. So again, any rules for multiplication also apply for division. So let's take a look at this count and name and how they interact with these numbers. So let's take something like 4 inches plus 7 inches. When we add those, what do we get? 11 inches, perfect. So if we look at our count and our name and we see what happens. We take our counts. We had 4 and 7, and what happened to those? Well, we combined them to make 11, right? We're adding here, so we combined them with addition. So we combine the counts. If we look at the names, we had inches, and what happened to those? Stayed inches, didn't it? Stayed the same. When we add or subtract, we keep the same name. Now you might be looking at that right now thinking, okay, that's maybe sort of interesting, but probably not quite worth your $300 for the course, right? Well, let's take a look at how multiplication is different. Let's take 4 inches, and I'm going to abbreviate, inches is just IN, times 7 inches. Are all of you familiar with the dot being used for multiplication? Yeah, same as the little x. 4 inches times 7 inches is, not everybody at once, there'll be plenty of time for everyone to participate. What's 4 times 7? 28, there we go. 28 what? Not inches, but inches squared. Good. Because if you think about it, multiplying, usually you're looking at like an area, you'd have 4 inches by 7 inches. You're going to end up with square inches, or inches squared. So if we look at what happened there, our counts are still 4 and 7. And we still combined them, only we're multiplying, so we combined them with multiplication. So we're still combining the counts. But our big difference comes right here with the names. We had inches and inches, and it became inches squared, or square inches. When we multiply, we also combine the names. And that is our big difference between addition and subtraction and multiplication and division. With addition and subtraction, we keep the same name. When we multiply or divide, we combine the names. Now again, you might be thinking, what's the big deal? Well, when we look at our other forms of numbers, it explains all the special rules that we have for those come from that simple concept. In fact, this even determines what we can and cannot use in each of those operations. For example, let's say I have 4 cows plus 3 boys. Do I get 7 cowboys? Does that work? Not really, right? How about if I did it the other way? 3 boys plus 4 cows. Do I get 7 boy cows? Anybody with a farm background in here? A couple of you? You can tell me that is a whole bunch of bull. Okay. Long way to go for a joke. But there's a point behind it. I may have mentioned it already. I'm a math teacher, which means I'm required by law to have a really stupid sense of humor. You'll get used to it. But there is a point here. When I add numbers, I'm going to keep the same name, which implies that I have to start with the same name. I could add inches and inches because they're both inches. I cannot add cows and boys because they're different names. Which one do I keep? Well, in order to do that, they have to be the same, so I know what to keep. On a little bit more practical side, I might have 5 feet times 2 pounds. Or not times, plus 2 pounds, I should say. When I go to add 5 feet plus 2 pounds, what do I get? I get 5 feet and 2 pounds. They're different names. Feet and pounds are different names or different labels. I cannot add those. However, when I multiply 5 feet times 2 pounds, when I multiply, I'm going to combine the counts. 5 times 2 makes 10. But I'm also going to combine the names. Feet times pounds is foot-pounds. If you're familiar with engines, that's a unit of torque. Or if you're in construction, that's a unit of bending moment for beams and stuff like that. When I multiply, I'm going to combine the names, which means I do not have to start with the same names. Let's look at how this affects some of our other forms of numbers. Let's jump right to everybody's favorite type of number, fractions. Yeah, I saw the looks. I know that's a little sarcastic. If I were to ask people on their way in the door what they dislike most or what they struggle with most in math, 4 out of 5 people would say fractions. So if you struggle with fractions or don't like fractions, be assured you're not alone. The top number of a fraction is called what? Numerator. Very good. Bottom number? Denominator. There we go. My little pause there reminded me of something. Something I should note. I am a horrible speller. You'll see me pause in the middle of a word like that sometimes, which means I got halfway through it and I forgot how to spell it. Also, I know my handwriting is sometimes a little sloppy, or sometimes a lot sloppy. If anything ever appears up on the board that you can't read, I assure you it was intended to be in English, but I either just misspelled it or wrote it too sloppy. I will not be offended if you ask me what something says. Just please interrupt me and just ask me what it is. So anyway, we have our numerator and denominator. What does it mean to numerate? Well, every 10 years, our government does the census. So they send out people to enumerate the population. What are they doing? They're counting. The numerator is a count. Probably already guessed where this next one's going. We have different denominations of money, different denominations of organizations. To denominate means to classify or to give a name. So the numerator and denominator are just a count and a name. A lot of people look at a fraction and they see two numbers. It's not. It's a single number. Just like having 4 inches or 4 cows, here we have 4 sevenths. So the 4 is an amount. We have 4 of something, and the thing we have is sevenths. We'll define what it is to be a seventh when we get into fractions in more detail. But for right now, let's just look at a couple of examples here. So if I add 4 sevenths plus 2 sevenths, way back in about 3rd grade when you first started working with fractions, that 3rd grade teacher says, when you add fractions, you must have same denominator, common denominator. That's not a special rule for fractions. Any number, when we go to add, we must have the same name. When we add fractions, we must have the same name, or common denominator. So then that same teacher told us when you add fractions, you're going to combine the numerators, right? Add the numerators. 4 and 2 make 6, and keep the common denominator, sevenths. Again, that's not a special rule for fractions. Anytime we add numbers, we combine the counts, and then we keep the same name. What if I have 1/3 plus 2/5? Can I add those the way they're written? No, because they have different denominators, they have different names. Again, nothing special for fractions. Any number, we have to have the same name to combine them. So let's look over on the other side here. Let's say I was multiplying 4 sevenths times 2 sevenths. When we're taught to multiply, you're taught to do what? Multiply straight across, right? Numerator times numerator, 4 times 2 is 8. Denominator times denominator, 7 times 7 is 49. Well, again, that's not a special rule for fractions. Not just because your 3rd grade teacher said so. It's because when we multiply any number, we combine the counts, then we also combine the names. So if I looked at my 1/3 and my 2/5, if it was 1/3 times 2/5, do I have to have a common denominator to multiply? No. Again, nothing special for fractions. We don't have to have the same name to multiply. We could do the feet times pounds. And just like any other multiplication, we're going to combine the counts. 1 times 2 is 2. And then also combine the names. 3 times 5 is 15. So all those special rules you were taught for fractions are not special for fractions. They're the same rules as for any other form of numbers. It just looks different because fractions look a little different. Let's check out another form of number. Let's look at decimals. So I put down 0.21. What's the formal way of pronouncing that? 21 hundredths. There we go. When we write it that way, it now becomes obvious that there's a count and a name. 21 is the count, name is the hundredths. So if I were going to add decimals, let's say I have 0.21 plus 0.3. Is that going to work? Why not? Decimal points don't line up. We've always been told when we add decimals, we have to line up the decimal points. Why? 3rd grade teacher said so. Well, again, if we look, we said that this was 21 hundredths. This is 3 tenths. They have different names. Fortunately, all we got to do is that. And now this is 30 hundredths. Now they have the same name. And when that 0 is there, the decimal points automatically line up. So lining up those decimal points is nothing more than making sure they have the same name. We go to add. We've got 1, 5. Where's the decimal point go? We move it straight down. Again, that's not a special rule for decimals. When we add, we keep the same name. Bringing that decimal point straight down is keeping the same name. 21 hundredths and 30 hundredths better give us 51 hundredths. So again, no special rules for decimals. When I multiply 0.21 times 0.3, do I have to line up my decimal points? No, because when I multiply, we do not need the same name. Again, nothing special, same as for every other number. 21 times 3 is 63. Where does my decimal point go? It's 3 spots over. So I got to put a 0 in there and then put my decimal point. Why? Okay, yeah, you were always taught you got to count 1, 2, 3 decimal places in the problem. So you have to have 1, 2, 3 decimal places in the answer. And that's exactly it. We're combining the names. This is hundredths. This is tenths. We combine the counts. 21 times 3 is 63, but we also combine the names. Hundredths times tenths is thousandths. So counting those decimal places is just a shortcut for combining the names. Let's look at algebraic numbers. Oops, people always get nervous when they start to see that. We got letters in with our numbers. 4x. 4x, again, is just a count and a name. So 4 is our count. X is our name. So just like 4 inches, 4 cows, 4 sevenths, it's 4x. It's a count and a name. The difference is we know what a cow or an inch or a seventh is. We don't know what x is. But it doesn't matter. It still behaves exactly the same way. If I have 4x plus 9x, what do I get? 13x. Good. I combine the counts. 4 plus 9 is 13, and I keep the same name. So what if I have 5x plus 2y? What do I get? I get 5x plus 2y, yeah. Exactly like my 5 feet and 2 pounds. I could not combine those because they had different names. Same here. 5x and 2y are different names. I cannot combine those with addition or subtraction. Let's look at multiplication. If I have 4x times 9x, what do I get? Well, 4 times 9 is 36. And just like inches times inches became inches squared, x times x becomes x squared. Same rules as for whole numbers. If I have 5x times 2y, can I combine those? Yeah, when I multiply, I don't have to have the same name. So I'm going to combine the counts. 5 times 2 makes 10. And then just like feet times pounds became foot pounds, x times y becomes xy. Any questions? Now again, hopefully none of that's terribly new to you, but maybe just a different way of looking at it. You might be thinking, well, that's maybe a little bit interesting, but how does that tie in with the numbers I work with every day? And the concept that ties this all together is the concept of place value. Kind of like the concept of a number. Place value is another one of those very, very simple concepts that's not usually completely understood. I'm going to try to go through this quickly so I don't insult you guys, because I know you've seen this before. But we're going to start at the end of a number and work our way backwards. So starting here at the end, what's this last place value? Hold yourselves back. What is it? It's the ones, right? Then what's next? Tens and hundreds. And those are actually the only 3 place values. They get repeated over and over again. Ones, tens, hundreds. ones, tens, and hundreds. And over and over and over again. This is our base group here. This is the thousands group. This is the millions group. Then it would be billions and trillions and quadrillions, quintillions, and on, right? If any of us ever have to go past 100 million, you can hire somebody else to do your math for you, right? So, to name a place value, we name its place and its group. So this here would be just called the tens place, where this would be the 10,000s, and this would be the 10 millions, and so on. I'm not going to insult you by going through how you pronounce a number. I'm just going to assume you guys can do that. But there are a couple of things about these place values that I do want to point out. One is, what if I have a number like 4,276? We are used to seeing, now obviously that is pretty simple with it written over the place values. But we're used to seeing it like that. But that is not the full number. That is an abbreviation of the number. The full number looks like this. 4,000s and 200s and 7 tens and 6 ones. A lot of you have probably seen that described as the expanded form of the number. And it's really just, it's the full form of the number. We abbreviate it like this because the location in there tells us what its value is, because we know those place values. If I have, going the other direction here, say 4,000s and 9 tens and 2 ones. What's missing there? Could I write that as just 492? No. There's a place value missing. What is it? The hundreds. So when I write in it in full form like this, it's just fine to leave it that way. Because each number is labeled, I don't need to put in the hundreds. But if I'm going to abbreviate it, I have to put in a 0 to hold that hundreds place. What you can see by putting in these expanded form, my main purpose for putting in this expanded form is so you can see that each digit here has a count and a name. This is 4,000s and 200s, 7 tens, 6 ones. Each digit has a count and a name. And when we come back in the second hour and start looking at our basic operations, that's going to explain why we work with things the way we do. Another purpose for our place values is another basic function, and that is, let's say I give you 4,753 and I ask you to round to the nearest 1,000. Well, what would that round to the nearest 1,000? 5,000. Very good. What that means literally when you're asked to round to the nearest 1,000. A lot of our basic functions in math refer to a number line. What this is saying is we have a number line that is numbered in thousands. And it's asking us physically which 1,000 is it closest to. Well, 4,753 is somewhere in here. It is physically closest to the 5,000. So that's why we rounded it to 5,000. Now, obviously, you guys don't want to draw out a number line every time you round numbers. So how were we taught to do this? Well, rounding to the nearest 1,000 means the first thing we're going to do is identify what the thousands digit. What digit is in the thousands place here? The 4s in the thousands, or the 1,000s, right? So that's the first digit we're concerned with. And there's only one other digit that matters in this whole number, and that is the next digit. The 4 here in the thousands place tells us it's between 4,000 and then the next number up, which is 5,000. This next digit is the 7, which tells us how far in between them it is. 1, 2, 3, and 4 would obviously be closer to the 4,000. 6, 7, 8, and 9 are obviously closer to the 5,000, right? Well, that's a 7, so that tells us we go up to 5,000. Hopefully that's not anything new, right? Okay. What if it were a 5? What if I asked you to round the same number to the nearest 100? 4,753. Well, I identify my, which digit am I going to identify here? Hundreds place, which is 7. I look at the next one, that's a 5. Well, 5 is right in the middle, isn't it? What do we do with it? We round up. The 7 tells us we're between 4,700 and 4,800. The 5, even though it's right in the middle, we've always been told that you have to round up, 4,800. The reason for that, of course, you may not have ever seen this. 4,750 is right in the middle, but it's not 4,750. There's digits that come after it. So the main reason we always round the 5s up is there's usually stuff after it that puts us past the middle anyway. The only way it would be exactly in the middle if that was 4,750. And even then, we would round it up. I'm not going to spend any more time on rounding because I know you guys have it. But I am going to make a note. If you get into machining, precision machining, or mechanical design, and even in some of your more precise welding applications, there are some times where you don't always want to round 5 up. For example, if you're looking at things, a lot of your measurements end in 5. So if you have measurements like this, on a part where you're adding, you have those dimensions that kind of come together and you're adding them up. If I rounded this to 2 decimal places or to the nearest 100th, we haven't talked about decimals yet, but if I rounded it to 2 decimal places, all of those would round up, wouldn't they? If I'm adding these, we get what we call a tolerance buildup or an error buildup, where those rounded numbers build up and we end up with a result that's a few hundredths bigger than what the actual result should be. And in most applications, that's okay, but if you're doing some very precise machining, or like I said, even in some very precise welding applications, that buildup can be more than what we want it to be. In here, whenever you see a 5, you're always going to round up. But I just want to make you aware that there are some processes where you'll see that 5 and sometimes you'll round it up and sometimes you'll round it down. I'm not going to do it in class because I don't want to confuse any of you. But if there are any of you that are curious, let me know and I'll show it to you one-on-one. Okay, we're a minute early for our break, but it's 3:19. Normally we'll take our break at right around 3:20. We'll take about 10 minutes, so if you want to be back in here at 3:29, we'll start our second hour of class.